Hi, everyone. This is another episode in the story of designing multi-computation capabilities in Wolfram language. And let's see what we started off with trace graph, which we talked about last time. Is this new material for trace graph?
Yep. So last time trace graph didn't work in all situations, and now it does.
Okay, so I can run the code. Should I run this code? Okay. Okay, so here, what am I seeing here? So this is a pure drilling exercise, basically. There's no evaluation here. Is that correct?
Yep.
Okay. So if I were to just do, all right, so if I say trace graph, let's just start a new thing here. I'm just trying to understand, and maybe you've already got this, but if I say trace graph of f of ABC. Okay. So let me try to understand what this is doing. This is saying this is the drill down, this is the evaluation. Red means that is the result of evaluation. Is that correct?
Yep.
Does red mean it's a fixed point?
No, red means that that expression does not need to do any subsidiary evaluations.
Okay. I see. But then that is a reassembly arrow there. Is that correct?
Correct.
Okay, Nick, do you have any comments on this? Is this consistent with the kind of way you're doing it, or is this quite different from the way you're doing it?
Well, the way this doing it is actually how the evaluator doing it is doing it. I'm doing it just by looking up down values, up values, and so on directly.
So can I see your version of this thing? That hold on, let me just save this in the right place. Where do I want to save this? Do I save it under notes under meetings here, or do I save it under SW notes?
You can save it under SW notes.
Okay. All right. Okay. So Nick, do you have an analog of this?
Well, no, because I only multi-evaluate only concerned with actual evaluation, and I don't have just this pure drilling down an expression steps.
I see. So if you were to do this, what you would do for this is you would simply say, if I were to take your multi-evaluate, which of course is doing a multi version of things. If I were to take whoops. Wow, it's complicated. Okay. So let's multi-evaluate. Here, and I say f of ABC. This would do something completely trivial.
Yeah, it's just not going to do anything. Yeah.
Because, okay, but so if I were to do this, so let me understand this. So if I had to do 1 + 1 here.
Oh, it's also not going to do anything because plus doesn't have any values associated with it.
I see. So your thing is dealing with down value defined values, not down code.
Yeah. You can provide down. It's like a separate pattern as an option. What kind of sub-expression to evaluate?
Okay, but in your case, what you're saying is you've defined PLUS of x blank, y blank, colon equals, and now there's the down value there. And if I now do this, PLUS of 1, 2, is there a graphical representation that you have of this?
Yeah, just comma 3 on the graph in quotes.
Okay. And now graph will do we'll have an event there, presumably.
No, I don't have events. It's just basically gonna deduplicate some expressions.
Okay, but so this here, if I were to do this, and I were to say PLUS of 2, 3, I don't understand this. Why didn't that go another level? Why didn't that go down to the
Well,
actual?
You should specify how many steps you go, because this is not a fixed point. So like 2 steps.
So should it have gone down another level? Why didn't that go to fixed points?
It is a fixed point because plus doesn't have any down values again.
What do you mean? Oh, you mean that plus doesn't have down?
Yeah. So
wait a minute. What is this thing down here? This is the capital plus.
Yeah, that's the capital plus.
But why doesn't the capital plus just evaluate to 6 here?
Because I don't want it to without my permission, so to speak.
Okay.
If I have an option that's like evaluate pattern, and you can say evaluate pattern blank plus, then it will evaluate all the pluses too.
I see. Okay. So what this is showing is this is a multi-evaluation. So this is saying you can either go and resolve the 1 plus, or you can resolve that second plus there. And in this case, those get to the same result.
Yeah.
So in the graph case, I would deduplicate that, and it would show confluent behavior, basically. Right?
Yeah. Right.
Okay. So what you're emphasizing is you don't have, if you were doing single way evaluation, do you have a path graph?
Yeah.
Always. Whereas Ian does not have a path graph because he's actually showing drill down inside the expression. Is that correct?
Right. Yeah. Yes.
Okay, now Ian doesn't have multi-evaluation possibilities, right?
Correct. Trace graph is just the standard evaluator.
Okay. And what was the thing just yesterday where we were talking about traversal order in the case of map. Yeah, okay, fine.
Mm-hmm.
Okay. All right. So let's take a look. Let's understand. Okay, so this is Nick's multi-evaluation. Okay. So now here, let's take a look at this. Okay, so those are the drill down arrows. Those are the evaluation arrows. These are the reassembly arrows.
Mm-hmm. So that graph is a trivial evaluation, but if you look at the one above, there are non-highlighted dashed edges, and those are transformation rules.
What do you mean non-highlighted dashed edges?
So like from the Y to the X.
Okay.
The 1
to the 1.
And the F to the G.
Okay. So, I mean, if I might say so, graphically, this is sort of the wrong way around because the action is being, shown as almost nothing, and the inaction is being shown as a big thing. If that makes sense. It's just a minor point. But the action here, that's an event. In Nick's terminology, that's an event there, correct? Whereas all this drill down is not an event.
Right.
Yeah.
Right. So if this was a token event graph, we would have an event node in the middle of these. Is that correct, Nick?
Yeah, right. That's good.
Okay. So, I mean, just in terms of the presentation here, can you make a big, thick yellow thing that indicates something happened here?
All right.
See what I'm saying? I mean, just so we understand what's going on. And in a sense, what we want,
new color for those edges rather than just flipping the highlighted and non-highlighted that we have.
Yeah, it doesn't make any sense to do that. I mean, we want, I want to see where was an event, right? Because what's going to happen is when we go to multi-computation, to multi-evaluation, we're going to have parallel events.
And so do you actually want an additional node there?
I'm not sure. Probably yes, but I'm not sure yet. Okay. For now, let's not do that, I think.
I'll just style it different.
Yeah. Big, thick orange thing, Okay. But again, I'm already confused again, because red is an action color. And this is an inaction node, right? This is a node which doesn't change anymore, correct? That's a frozen node that does not change anymore, correct or not correct?
It doesn't mean that it won't change. It means that it doesn't need to do sub-evaluations.
Okay, it's the end of the line in terms of drill down.
Mm-hmm.
But you see, that's not right, because that's all end of the line in terms of drill down, right there. It finished drill down.
It's not going to do any sub-evaluations because it's going to apply a transformation rule.
No. We're not getting this right. Look. There's two different actions. There's drill down and there's transformation. Right? Okay. So I want to know, there is one thing as you reach the bottom of, okay, so normally we do transformation first and then we continue drill down. Is that right? In the evaluator.
You do drill down and then transformation.
Okay, so fine. So then to say this is very, very confusing and not right. This reached the end of the line in terms of drill down here. Correct or not correct?
Correct.
It's done with drill down. Okay, so why isn't it red? If you're telling me that red means it's done with drill down, it should be red here.
Right.
Okay. And then it has an event that transforms it. And then when it returns something, again, there really should be an additional node for the X.
So I guess red is both no further drill down and this is from a previous drill down.
That's not good enough, right? That's going to confuse things. We got to break it apart to the absolute minimal thing, right? No combined colors. Okay, we have to, the whole point is we're trying to get this so that every step is separately represented so that we can see what the multi-way version of it is. Make sense?
Yep.
So let's not combine anything. So here, for example, I don't understand why that X doesn't have an additional node for, well, no, that X is an end of line. Okay, so we just got the X. And now the next action is there drill down for the X? And the answer is no. Right?
Right.
That's the first thing it's going to do is try drill down, and it can't do it.
So you don't drill down in atoms.
I understand, but then why is this showing a 1 goes to 1? That's not right. Either it's got to show an X goes to X, or it shouldn't show a 1 goes to 1.
Well, so the highlighted dashed edges are for expressions that evaluate directly to themselves. They're represented as a singleton in the output of trace. I've only split them into two kinds of.
I don't care what the output of trace is. I mean, trace was something we designed in 1990. It's been a flop. So we're not basing what we're doing on trace. We're trying to actually get it right. So the fact that trace elided things.
Well, my point is I'm not making any decisions based on what trace does. So the thing is I'm choosing to represent an expression that evaluates to itself as two different nodes, just so that you see the node flipping from one color to another. Arguably, that's not necessary.
Yeah, I don't think that's the right thing to do.
And the reason I brought up trace was because trace doesn't do that. So
I see. Okay, but so again, I want to understand, because in the analogy of physics project stuff, okay. In the physics project, in a token event graph, okay, there is no drill down in the physics project, because the physics project is using hypergraphs that are one level. Am I making sense?
Mm-hmm.
Other people, Nick and so on, understand that, right? And so what we're doing there is we are taking we have a bag of tokens, which is the hypergraph, and we are then picking out, in some cases, pairs of tokens. Now, in the evaluator, we never pick pairs of tokens. We never do the thing that the physics project does. Is that a true statement? Nick, other people, you understand what I'm saying? In the physics project, we will, in a token event graph, we will be picking two different pieces. Oh, we have Jonathan here as well. Jonathan has opinions about all of this. Everybody's very silent. Okay.
Okay. My understanding is that that's correct. Like your transformation rules get applied to an expression in trace graph instead of, a collection of tokens.
Right. Nick, do you want to comment on that?
Yeah, it's only a single token or sub-expression that always gets evaluated in the usual trace.
Right.
So, like, for example, for Wolfram model, we have rules that act on different hyperedges. So it's like a multi-sub-expression evaluation.
Well, so what you're identifying is we've got two kinds of multi going on. Right. One, one is multiple possible events from a single expression, and we're doing all of them. And the other is events that have multiple token inputs, which is something which is not present. Is that true that that's not present? I mean, obviously you can write it trivially with pattern matching in the language. But the evaluator is not intrinsically dealing with that. Does that make sense?
Yeah.
So, I mean, that's another way in which we could generalize the evaluator, but it's not the one we were thinking of so far. Is that right?
Yeah, I don't think that we've specifically mentioned this in terms of generalizing the evaluator.
Okay, I suppose another way you could talk about that is you could say that you want sort of rewrites to whether or not a rewrite can be applied depends on multiple kind of non-local parts of the expression tree.
Exactly.
Right.
Right, which is not what we normally have. Normally rewrites are local. This is effectively
normally the rewrite is for the entire expression tree.
Or for a well-defined subtree.
Yeah, the entire subtree.
Right. i.e., rewrites not applied purely to subtrees. So in a sense, that's another specialness of the evaluator that we have right now, is that it is a pure gulp-a-hole subtree evaluator.
So if I can make just a purely pragmatic comment, so in for functions like find Wolfram model proof that take hypergraph transformation rules of the kind used in the physics project and convert them into things that can be over which one can do theorem proving using the standard WL evaluator, the way that that's done, which may or may not be optimal, but almost certainly isn't, is that there's a composition operation on the hyperedges, in effect, composition operation on the subtrees that's assumed to obey commutation to obey commutativity, and it's that commutativity operation that lets you effectively do this non-local rewriting.
Okay, so wait a minute. So basically, what you're saying is, you pick the things, you pick those sub-expressions up, you make them into a super expression, on which you then do rewriting.
Right.
Okay, so that is another stage. So a way can be looked at as an additional stage, which is collect the subtrees into a single tree, then rewrite. Right.
And again, the fact that the ordering of hyperedges doesn't matter is just stating that essentially that collection operation is algebra, is commutative.
Yeah, right. Right. Often consider order not to matter, although I'm not sure that that's I mean, I don't think that's necessarily an absolutely, yeah, I'm not sure that that's a necessary feature.
Oh no, I mean, obviously for a full evaluator, you wouldn't want that to be the case.
Right.
That's peculiar to the hypergraph case.
Okay. So, all right. So let's go back maybe and look at, so I mean, just in terms of where we're trying to go with this, again, the big picture is we are, okay, and again, I think we summarized this last time, so let me go back to that for a second to make sure we don't confuse ourselves. Let's see.
If you want to go to multi-computation and then meetings and notes, last week's detailed notes would be in there if that's what you're looking for.
Okay, I think I'm also looking for, okay, so these are, graph evaluation technologies, okay. Yeah, this is what I wanted to do. This is what I want to talk about. This whole idea, which I've been through many, many times now, of in the multi-evaluator, you know, again, we want to do this thing where we say essentially multi-evaluate of expert, and it produces some kind of computation object or something, and that thing is a lazily computed, could be infinite, could be non-terminating. And then we can ask of that computation object, we can say, e.g., you know, find a path from, you know, expert to expert 2, right? That's essentially theorem proving. That's essentially a theorem proving, you know, question, right? Which is otherwise known as the find replace path. Right? That's one type of thing. Another type of thing would be find an output that satisfies a given condition. Find an intermediate step that satisfies a given condition. Intermediate step or an output in the multi-way thing that satisfies a given condition. Does that make sense? That's like optimization.
Yep.
Another thing would be kind of find the probability for a particular output or one satisfying a condition. Okay, so that's like probabilistic programming, and then there's, you know, question mark, path counting, and so on, how you do the path counting, but that's basically that. So a subcase of that, or the kind of hash P computation of count the number of outputs of that type. So actually, you know, in a sense, I think this is like NP computation. Is that right? And this is, I mean, I think you can think of these in terms of computational complexity classes to some extent. Anybody got any more thoughts about that? Anyway, so look, this is the kind of thing we're trying to do, right? Does this make sense to people? And yeah. I mean, another thing we're trying to get as output is a graph that represents the multi-evaluator, the result of multi-evaluation to some level. That makes sense?
Okay, but we have that to some degree already with Nick's function.
I know, it's just not finished. I mean, that's the point. We're getting there. We're trying to figure out what we're doing there. We don't have the whole thing because we don't have something which runs to the conceptual fixed point, which may not exist. Because, you know, if I run multi-evaluate on the S combinator with some complicated initial string, it's not going to terminate.
Yeah.
Right. So what do we do?
Well,
Right. And
use
that's
the
where we
lazy
have
approach. Yeah. Right.
Right. But we have to know what it is we're trying to extract from it.
Right.
And for that, you know, when there is a fixed point, when there is a single fixed point, we don't care about traversal order. Well, we might care. We don't care about traversal order except for efficiency. Right? But in the case where there isn't a single fixed point, we absolutely do care about traversal order. We care about which foliation we're looking at. We're going to get a different answer.
That's right.
Okay.
So one question I have is with the version of multi-evaluate that Nick's sharing with us, it only goes to a fixed point, like the addition actually evaluates when Nick basically permits it to do so manually. So if this is going to work in general, how do we overcome this obstacle where we're letting it evaluate by specifying that it can do so manually?
Well, okay, hold on. So the question is, what can be in, okay, so what can be in EXPA in multi-evaluate? Okay. So clearly, you know, by hand transformation rules are fair game, right? We know we're going to have those. We also want to have built-in evaluation rules, built-in transformation rules. So the question is, how do we represent those in, and I claim a built-in transformation rule is like, you know, for theorem proving, it's like, what do they call it? Hammers or something. I don't know what they call it. You know, it's something where you kind of, you know, you're just jumping to the answer, right? With a built-in transformation rule. Now, there may be a more complicated case. Okay, so here's an example of okay, so the intermediate case is, so a built-in transformation rule, like 1 + 1 goes to 2. We think that's a fairly safe thing to put in there. Okay. However, let's say it is a sandwich of rules, e.g., you know, nest of f, comma, whatever, where f has by hand transformations.
Okay.
Is that making sense?
Yeah.
So that is reminiscent to me of things that we have in neural nets where we've got some meta operator. Anybody want to comment on this? So this is a case where, Nick, have you thought about this case? And is this what's holding you up? Because I mean, you know, by hand transformation rules, we understand how that's going to work.
Yeah.
And the second case here, if you just say it's done in one step, we understand how that can work too, right?
Yeah, we can in principle add our additional down values, basically. That's what it is.
Well, yes, but it's when it's a built-in transformation rule, it's just like you just run the code.
Yeah.
Right. I mean, in other words, if it, I see. So the way we would do this is there is no user code that is run automatically. It is only run in the harness of multi-evaluate. But the question of whether the built-in code runs automatically is its own question. And now we've got the sandwich cases. Hey, does Christopher, for example, have any opinion about this concept of the, or anybody else here?
By hand, do you mean you would give a list of rules as another argument in multi-evaluate?
Well, that's a possibility. E.g.,
or do you mean
no? I that was well
defined symbol,
right? E.g., from an explicit list of rules, or from down value assignments.
Well, can we just say like symbol definitions to be complete?
What do you mean?
Well,
instead of
down values.
Yeah, okay.
That's just one kind of definition.
Okay. Okay, so I think
so one of the things we
yeah, go ahead.
Well, one of the things we talked about a while ago was sort of, but I'm not sure it can actually work, was something where basically you'd write sort of a normal program, and then every so often maybe you could use some construct, like, I don't know what to call it. Let's say like multi or something. You'd say multi of, you know, and you give it a couple of arguments, and then effectively that would be, you know, a point where the program would sort of branch, and it would, you know, you could think of it as non-deterministically choosing, you know, one of the arguments there. But I don't know, there were sort of lots of issues with this, like the fact that, you know, if you're using this inside of, say, a module, then the module variables, you know, as it goes through the different branches of the multi, it somehow needs to be able to, you know, reset the module variables and so on, because, you know, if one branch changes the variables, then when it runs the next branch, it'll be all messed up. And so, yeah,
but
I mean, it would be nice.
We
if
understand that
like
case. That's exactly Nick's canonicalization of bound variables stuff, isn't it? Nick, can you comment on that? That's exactly when you have a multi-way system and it has generated variables on different branches. That's the question of canonicalizing the variables on different branches, I think. The thing Christopher just described.
Well, if it evaluates in different branches, it may as well evaluate independently, so I don't see an issue at all.
No, because the problem is that if you have an outer module, like if you set a variable x, and then in one branch, it's going to reset x to 12, and in the other branch, it's going to reset x to 15, right? Then if you run the first, depending on the order in which you happen to run the branches, you know, you might get sort of weird conflicts.
Well, yeah, you should maintain the state. So each of those branches should have a state.
Right,
but
the problem is there's no easy way in the language right now of being able to represent the state, right? Because it's just like the whole symbol table.
Mm-hmm.
Right, and you'd have to branch it by a submodule that has its own separately named X, I think.
Right.
That would be a way of doing it.
From a programming perspective, if you know about this issue, it's not hard to just basically make sure you don't do any closures, is effectively what this is. But I'm not sure you can really trust people to know that.
Right. How do you get a dingbat? I always forget this. And it's a star, right? No? How do you get a
Yes, it's a star.
What do you do?
You want a bullet. It's a star. You just type a star in a new cell.
What? In a text cell?
Or is it input?
I think it's I mean, first, if you just
there we go.
star,
I got it.
Yeah.
Okay. All right. So the first way to specify multiness is an explicit list of rules that will be used at each step that can be reused. No, can be an explicit list of rules.
Can be tried, yeah.
Yeah, can be tried at each step. That's one form of multiness. And that's what we were imagining in e.g. find replace path. That was what we were imagining it was going to do. Make sense? And that is also how the automated theorem prover will work, if I'm not mistaken, without any hammering, right? If you know, the standard automated theorem prover, what is this? This is essentially find equational proof here. Am I right?
Actually, yeah, can I make a comment regarding that? So in terms of the built-in transformation rules, one thing that would be really convenient for theorem proving is if we are going to have those, that one has essentially fine-grained control over which ones get applied and which don't, if that makes sense.
Yes.
Right. You want your theorem prover to be able to say, yes, I can use the fact that addition is commutative, but I can't use the fact that, you know, I can't use this complicated theorem from analysis or something. Where the evaluator might treat both of those things as being somehow on the same level otherwise.
Yeah, no, I understand. I mean, that's a huge can of worms. That was a thing in SMP again, where I had names for all the transformation rules that were built in, which we gave up on here. But yes, I understand. So okay, so another thing is okay, so adding built-in transformations. So now the question is, how does that work? So the question would be, which transformations can you use? Which transformations can be used? And then what happens in the sandwich case? In the callback/sandwich case. Because in other words, in a sense, find replace path is a sandwich, but its only sandwich operator is composition. Am I right there? People understand what I'm saying? I mean, so in other words,
do you mean that you're using built-in system definitions as well as users?
Yes, I mean a sandwich. I mean something like nest, where the function that is being used in nest here is something that has user definitions. Okay, so the whole point is that you should see, in other words, okay, so the basic point is there's controlled stuff in F. F has sort of controlled pieces, but they are being sort of bank used by nest. Is that making any sense? I mean, it's just like in a neural net where you have something where you have one of the meta operators for neural nets that's saying, use this network in a recurrent way or something. Well, okay, let's talk about multi for a second. Maybe that will make this clearer. Okay, so then there's multi. And, oh gosh, you see, there's other cases here because, okay, there's another case which is, sort of do evaluation of arguments in any order. That's another multiness. So in other words, if we
but by do you mean, yeah, go ahead.
Was that like the argument concurrent attribute?
I don't know. Oh yes, right, exactly, yes.
Well, no, but that doesn't affect the output you get, really. I mean, assuming that there isn't like crazy race conditions, or assuming you wrote your program correctly, that doesn't affect the output. It just affects the internals of how it's done.
But it does affect the multi-array graph, right?
Why?
Because
I mean, you just mean it affects it in the sense that
that affect output, assuming there's a fixed point.
But like, isn't this just if you look at like if you look at say the trace graph, right? I mean, it's just that there's all of the drill down edges. All that attribute means is that you do all the drill down edges at the same time in different threads, as opposed to doing them sequentially. But it doesn't actually change the graph.
Right.
Yeah, I guess that's right. But yes, okay, fine. Yeah, okay. Right. Okay, so it does not affect the evaluation graph.
I guess it would if you had some shared variables and you wrote your program poorly. But
only, yeah, assuming no side effects.
Yeah.
Well, multi-way graph still gonna have branches.
Yes, but the branches will be the same. But wait a minute, but only the foliation used.
I mean, like each branching evaluates arguments. They like separately. No, we just evaluate each argument individually.
Yes.
So they're different.
Right.
Yeah,
go ahead.
Sorry, I was just going to say, this is probably a question for a different time, but is there an argument given this to have a finer grained version of a multi-way evolution graph in which effectively each edge is not an individual evaluation of an argument, but an evaluation of all arguments in some sub-expression that leads to a fixed point, so that the only branches are genuine branches of non-determinism?
Wait a minute. So you're saying.
So, I mean, this would be the full expression analog of a generational multi-way system.
In which, so by generational, you mean that the whole sub-expression has been reassembled. That's what you mean by generation.
So if you've got you have some sub-expression that's f of a, b, c, d, and you know that the evaluation of that sub-expression reaches a fixed point, then rather than having individual paths started for evaluating a, b, c, or d initially, you just evaluate the whole thing to that fixed point and treat that as a single edge.
Right, but that is basically, if I'm understanding correctly, that is generational. That's saying it's a multi-way system where every step is a generational step.
Right.
So this is.
But the thing is, with generational multi-way systems, as with all multi-way systems, we kind of don't worry about whether the thing reaches a fixed point or not. Whereas, if you want to turn this into a practical evaluator, you would have to.
I'm not buying the fact that an evaluator has to have a fixed point. That's the point.
I'm not claiming the evaluator has to have a fixed point. I'm saying that if you want to do reasoning over these things, whether the individual subtree over which you're evaluating has a fixed point or not matters. Because if you take the combinators example, if you want to reason about intermediate expressions, then it matters whether the subtree you're applying things to is going to terminate or not, because the confluence properties will be different in that case.
Okay, but so what you're saying is there a larger lump multi-way system in which, so this is in which you aggregate, congeal, what's the right word? You not quite conflate, in which you pull together sort of sub pieces of the multi-way graph that essentially correspond to drill down. Is that right? That correspond to roughly correspond to drill down. All right, let me just try to understand the multi concept for a second, because I think that might be helpful. Okay, so what does multi do? So multi says, what would be an example of where one would use multi? One just says, one's reached this point in the computation, and you say you either do f of x or you do g of x here. Is that right?
Yeah. So you just say, multi of f of x comma g of x.
Right, and so in that sense, so CF, ABC, AB has A and B space-like separated. Multi of AB has A and B branch-like separated. I think that's what we're claiming. And so then the idea is that this is a way of putting together, so in Ian's pictures, no, not even Ian's pictures, in Nick's pictures, oh, this is so confusing. Is that a more granular way to write this branching? That we could say this thing evaluates to multi of this and this. See, I think multi is going to get confused because I think it has to have a foliation. In other words, to say, okay, so let's put it different way. As we do a computation, we reassemble things into spatial pieces. Which thing is that, like, consider combinators and consider some multi-way graph of combinator evaluations. The assembly of a particular complete combinator expression will get a different expression. Yeah, I mean, it's until we get to a fixed point, there's no guarantee that we'll have one of these expressions could have this part not yet evaluated and the other parts evaluated, or something different.
That's right.
And so both the spatial and the branchial sort of intermediate steps depend on foliation. And the question is it useful? What we are doing right now is we are very fixed point thinkers, so to speak. And so we take, we think there's a reality to the spatial version of expressions. Even though in fact, if we had a multi-way evaluator, there wouldn't be a reality to the intermediate expressions. Is that making sense? In other words, the fact that there exists ever A, B, C, D in an intermediate step, it might be fictional. Because if we're doing...
Where do you, if you need this foliation, but where is it specified then in the version where you just give a list of replacement rules?
Well, the whole point is that you can never really ask what the intermediate expressions are, because with a set of replacement rules, you could have applied rules 1, 2, 5. You could have applied 1, 1, 7, 5, 1, 2. You could have applied them in different orders. Every branch applies them in a different order.
Well, surely you can ask what the intermediate expressions are, but you'll just get a branchial graph.
You'll get a branchial graph, right? But you'll have many different possible intermediate expressions, right? There isn't. Whereas, okay, in the evaluator right now, okay, I mean, our evaluator has just a particular set of intermediate expressions that correspond to its particular traversal order and its particular rules.
Can you open the sections for hold attributes and non-standard evaluation?
Yeah.
Because I think viewing it as a traversal order might be too restricted.
Oh gosh, really?
Mm-hmm.
What should I be looking at? Well, let's look at non-standard evaluation here.
Right. So here we're seeing subsidiary evaluations that are not just traversing the expression that you started with.
Okay, that's what I've been calling sandwiches over here, I think. In other words, there's a control of the evaluation that is happening through a built-in function that isn't just defined by a generic multi-way graph.
Mm-hmm. So, for example, look at the very last step. You have 2, which is the result of u equals 2, and then null, which is the result of the do, and then 256, which is the result of u. And this recombination edge, unlike the ones above that were just building an expression, compound expression has a special way of reconstructing this, where it takes the last thing.
Right.
So that's special deconstruction and reconstruction.
Right. That is sandwiching. Not a very good word for it, but you get what I'm saying. That's something where, yes, where there's an overarching control. Okay, so my claim is that the pure case of you've given a list of transformation rules has a default way of deconstructing and reconstructing that is in a sense trivial.
And can you scroll down in the agenda?
Mm-hmm.
For the evaluator style replace. Or yeah. This is just some basic code that is the basic idea of how the evaluator does its traversal.
What should I see here?
I think you should read the code. Like the definitions. So you're taking a fixed point of repeatedly applying rules, but the way you apply the rules is by evaluating the parts at level 1 and then applying rules to the thing you get.
Right. In other words, that's just saying a non-held function, a non-hold function evaluates its head and its arguments and then tries to evaluate the whole thing.
Yep. And then it does a fixed point of that operation.
Yes. So this is the Okay, but the whole point is this thing, evaluate the head, evaluate the arguments in sequence. That is precisely a particular foliation of this multi-way evaluation. Because that's the thing which, if we had multiple threads running, we could evaluate the arguments in different orders. Right. That's a particular order where you're going essentially left to right.
Mm-hmm. And in the case of non-standard evaluation, you can have completely arbitrary expressions to be evaluated and arbitrary to do with them.
While we're on this borderline observer theoretic thread here, I wanted to mention, Nick, I don't know if we're comfortable discussing it yet, but Nick did mention to me that he has an idea for equipping multi-evaluate with the ability to also, you can specify the kind of search like breadth first or depth first. And so it can kind of impose some sort of ordering as it's performing the multi-evaluation. This is kind of fresh. I don't think it's been developed yet, but maybe we could discuss it.
Well, but that's essentially saying, look, one thing is in this model where multi-evaluate returns a computation object, that's a lazy thing. What I think you're saying there is, what does the front look like? In multi-evaluate, if you're doing breadth first, it will have a particular front as it goes, multi-evaluate as it iterates through what it's doing.
Right.
It's going to have a certain front. If it's depth first, it'll have a different front.
Yes.
Is that right, Nick?
Oh yeah, right now it's just breadth first, which way it evaluates all the sub-expression in breadth first order.
Right, but so in principle, you could use Ian's traversal order mechanism, possibly even very directly if we had a traversal order for map, you might be able to plug that in very easily to your code.
Well, not necessarily, but yeah, it's easy because it's as soon as I have a list of expressions in each positions, I can sort them by whatever order I provided.
So something worth pointing out is, so like with tree traversal order, there are traversal orders that are not defined by sorting the positions, like leaves first.
Right.
And that might be just totally uninteresting for...
I'm not sure. No, I don't think it's necessarily uninteresting. I think
you need it to be you need the entire multi-way system to be finite to be able to do a leaves first.
I see. Which we probably don't have that. Okay, but so look, in terms of what we want to do here, it seems to me, why don't we develop something where we are giving explicit lists of rules? Why don't we make sure we can really do that case? And why don't we build the functions around that case, like find replace path? Because one of the things, if I'm understanding correctly, the explicit list of rules, okay, that would be the case that we need. Well, for theorem proving, with traditional theorem proving techniques, we need two-way rules. Correct?
Well, that's what we've been using.
Depends what you mean by traditional theorem proving techniques.
Explain.
Well, there are theorem proving techniques like paramodulation that require two-way rules. There are others like resolution which don't. They're both traditional. In the sense they've both been around for about half a century.
Right. Well, but then, so what I'm suggesting is, can we get a version of, whether it's multi-evaluate and then you do things to its lazy computation object, or whether they are particular functions like find replace path. We've got a version of find replace path. We have multiple versions, but can we please just try and finish that off? In other words, try and work through the cases for explicitly given rules, which is more similar to what we've done in the physics project. Then we've got the separate issue of dealing with the interaction with our built-in evaluator technology. Am I making sense? Nick, do you understand what I'm saying here?
Yeah.
So the things you've got right now, how much does your multi-evaluate basically do? We've got these different cases of what you're trying to get out, right? Can we do that from your multi-evaluate or not?
What different cases?
Well, I mean, things like the find replace path, right? Just find a path from here to there. I don't think you can do that from this yet. This is just evaluate and generate the whole multi-way graph. Is that a correct statement?
Well, it depends how efficient you want it to be. It's like, in order to make it into a semi-efficient find replace path function, you just need some kind of selection, right? So that you not exploring every branch.
Sure, absolutely. And we had a couple of implementations 6 months ago of find replace path that, for example, went, knows it's going from the input and it's coming, and it then is the past light cone of the output and so on. It's trying to look at the overlap between those two things. I mean, we just need an efficient version of that. And that efficient version should be essentially the theorem prover, shouldn't it? Am I confused there? I mean, isn't that what a theorem prover is, basically?
Yeah, it's just not usually doing it like that, like future and past entailment cone and intersect and tries to find an intersection, right? Because you can't usually go backwards.
Well, you can if you have two-way rules.
Oh yeah.
Right, and if you recall, the very first prototype version that I made of find replace path and find string replace path did exactly this.
I know. Right. So I mean, I'm saying, let's have a version of find replace path that is efficient as it can be, given that if it has two-way rules, it can do the forward backward thing. If it has one-way rules, it can't do that. It has to have some other selection criteria and so on. But then the thing is that find replace path, as we know from the very beginning of how we were doing this, one thing we can do is just give the path. The other thing we can do is, there are other elementary things like the length of the path. The question, is there a path, right? Is this a possible output? Does a path exist? Other things are the path together with some stubs of the branch shield pieces, which I think was also useful. Another question is just find me a path, any path. Another is find me the shortest path. Get what I'm saying? I mean, this is what we want to do. This is a style of programming. Is I've just got a bunch of transformations and I want to find things out. The things that we just listed here, right? This type of thing, right? So in other words, case number one is we've got a list of rules, one-way or two-way rules, and we want to do these kinds of we want to answer these kinds of questions for them. Does that make sense? I think, Nick, this is kind of in your area, because I think this is basically, sort of generalizations of multi-evaluate.
Well, I can imagine it as having a multi-object that you can query with all those different questions. And it's like,
yeah.
It's like you're constructing an observer, and it's some kind of agent that tries to traverse this multi-object. And
that sounds great.
Searches for things in it.
I think it's very
multi-object itself is lazy thing that just doesn't have anything. It just constructs a history of I don't know. It's maybe some interaction between this observer and the multi-object. Maybe there are different kind of things that we have to construct.
Yes. I mean, right. So in other words, you could potentially have a symbolic representation of the observer, which itself has operations done on it. So multi-evaluate going to multi-object can do some transformation. That makes sense? It does pre-processing so that the multi-object isn't just raw redoing everything there. Does that make sense?
Multi-object is like an environment that your observer is exploring.
Well, fine, but then the observer itself could have something where it, what am I trying to say? Where you can compute on the observer and pre-process the observer, just like you can pre-process the environment. Okay, but look, this is the thing we know we need, okay? So that's sort of step one. is we know we need these different cases of this. And, you know, so I think that's something we should build. Now, the next question is, so this is using by hand transformation rules, just from our pattern matcher. And I mean, one point to make there is replace list already is the core operation there that basically does, you know, enumerates the cases. Am I making sense?
Right. Well, multivariate already uses replace list underneath.
Yeah, I understand that, but that's the core thing that is multiing. That's the lowest level multiplication, so to speak, that has to be done with pure by hand transformation rules. Mm-hmm. What is less clear is how to do the multiplication when it isn't just a list of, okay, so look, the, you know, generating multiplication. Okay, so one method is use replace list. And that's what's going to be good for explicit lists of rules. Okay, the next case is that you are trying to do it, doing it from built-in data structures, e.g. a list, right? Where the multiplication is you can evaluate the elements of the list in any order, if I'm making sense. See what I'm saying? I mean, in other words, that's a different thing. Right? Did you understand what I'm saying? Anybody understand what I'm saying? This is a way, if you want to know what are all possible branches, right? One way you can do it is you use replace list and you use the fact that a rule can be applied in multiple ways, or multiple rules can be applied in multiple ways. The question is, what are the other ways in which there are multiple branches? One other way in which there's a multiple branch, I think, is that a list can have its elements evaluated in any order.
Well, yeah, that's the position, basically.
Or even just any expression.
Yes, can be evaluated in yes, exactly. But the point is that's and sometimes, okay, so my point is the difference between, so we've got this case where we've got by hand rules specified, okay? And that's a case where we think we understand what we're going to do. Do we understand what we're going to do here? Do we understand this stuff here? Yes, Nick, I think that's for you, basically.
Well, multivariate has all this multiness already. It's just not in this lazy fashion.
Well, I know, but it doesn't have the ability to say, find a path from here to there. Yeah. That's what we need. Does it, or does it have that? Does it have that or not?
No, it's just, well, if it's easy to add a selection function, it's kind of already some kind of criteria when how to find stuff.
Yeah, okay, fair enough. But I mean, so what it's doing right now is it's generating the graph, correct? Basically, it's generating the data for the graph, for the complete graph. Okay, so now we are doing the filtering by the observer of that graph. And as you say, it will be much more efficient if it is not generating the whole graph, but is doing so lazily.
Yeah, and with some order specified and other tricks.
Yes, I know, but that's going to be, you know, that is for the observer, that is a foliation taken by the observer on the multi-way system.
Yep.
Right?
Yep.
Okay, so now that's the case for by hand rules. Okay, the next case we're interested in is the case where there is something that where we have not just a bag of rules that are being applied. And but by the way, with the bag of rules, at each step, we're just doing /dot. Let's see, do we have any drill down issues there? No, the rules are being applied to whole expressions, aren't they?
It's replace, right?
Yeah, it's replace, right? So that's the case here. The simplest case.
Request list. So it's a request
Yeah,
list.
replace list, right. So the simplest case, all right, so look, drill down. Simplest case, pure replace list, i.e. whole expression replacement. Okay. Next case, some form of drill down or sandwich. Okay, so drill down is the pure, recursion, as Ian has indicated it over here, the pure recursion into an expression done by the evaluator. Drill down, wherever you had this example here, sandwiching is more like this kind of operation. So in other words, the one operation which you are indicating in these graphs is the pure drill down. This is, I don't know where there was an example of one, but the pure drill down, which you had up above here, wherever it is, there's pure drill down into an expression like this one here. Make sense?
Yep.
And then there is what we're calling sandwich, which isn't pure drill down. It's something else. It's a controlled way of going through an expression or processing an expression.
I think it's basically two different kinds of deconstruction. Do you deconstruct it into its parts at level 1, or do you deconstruct it into arbitrary expressions?
Perhaps, yes. But I mean, in other words, or alternatively, it is a thing where it's a pure atomic, operation done by the built-in code. That's the whole point. You're showing here. Okay, so here's the basic question. It could be the case that once you get into the built-in code, there's no multiness anymore. Okay, so this is a question. Inside built-in code, can there be multiness? Right? And for example, e.g. nest or nest list or something, nest f, x, 5. The f there could itself have multi-stuff in it. Does that make sense? Or we could decide that it can't have anything multi. Once you go into nest, it's a single atomic operation and there's no multiness anymore. Do you see what I'm saying?
I think it's more like if f was some kind of operation that involved multi-computation, like it would just be kind of self-contained. It would just, it's just another function. It's just f. Like, I don't think nest would even treat it any differently. Like if f's like a find replace
and we're
path.
making one of these graphs. Listen, if we're making a graph that shows the multi-way graph of what goes on, right? There's the question of, is this just a subgraph? Is the f piece in the nest, is it just a subgraph, or is there something more complicated going on? See, because otherwise it should be the case that the events that we produce, there could be an event which just represents that was a built-in operation, and that's the end of the story. That's the only thing that happens there, is a single built-in operation. But in compound expression, for example, there isn't just a single, you see the innards of that. Do you get what I'm saying?
Right.
Yeah, I understand.
So with non-standard evaluation, you could have arbitrary expressions and arbitrary handling of them.
Yeah, exactly. So the question is, how does that merge into the multi-way graph? And that's essentially what we're also asking over here, because you've got drill down. How does drill down merge into the multi-way graph? Does that make sense? I mean, here you've got this is yet a different case, because this is down values instead of rules. Or maybe this was done with rules, I'm not sure. Am I making sense? I mean, this is a picture that you get by doing the multi-way graph from a collection of replace list applied rules. Is that right?
Looks like it.
Well, this one is made with rules, explicit rules.
Right. Okay. So my point is, if sandwiched inside here, there was a nest operation, what would this look like? See, would the nest operation just be a single event, or is there something inside that?
Yeah.
Yeah, I think you would just see a node that has head nest and then an event and then a new node that doesn't have the head nest anymore with no sub detail.
If the nest were a pure function, then it would be just another path, because each application of nest is just another rule. For example, if it's nest f x5, it just getting replaced with nest f of x4, and so on. That would be the ideal case. But if we don't have an explicit rule for nest, then I have no idea.
Wait a minute. Look. The problem is we don't have, we have a large system which contains many black box, essentially laws of inference that are not, we have laws of inference that are explicit or something that correspond to the, you know what I'm saying, to the to explicit rules.
It's the difference between down values and down code.
Yes.
Or even like maybe you don't even want to be able to see the down values for things that are defined in top level that are built in. Isn't there an option?
Oh, right, exactly. That's like the debugger. That's like the issue we have with the debugger is what do you want to see? Right. So we can have, the other case. Okay, so we've got the replace list case. We've also got, or we've got down values, either all or user supplied. Okay, and I think that case we should also try to support, because you can get those down, and maybe you support it as a practical matter, and Nick, this is probably for you, by just clearing the symbol and looking, by just looking explicitly at the down values list, because you don't actually want to use the evaluator. Am I making sense?
Well, that's already what I'm doing. I think I'm not using evaluator.
I know you're not. But I'm saying if I've defined a Fibonacci function, f of x blank colon equals blah blah blah, right? Mm-hmm. But I want to use your code. I would like to be able to just say multi-evaluate of f of 7, and not write it out as rules, but have you deal with that. Right, by not using, by having it doesn't use the evaluator on f of 7, which would use the down values that have been defined, but instead you use the down values by hand. Do you get what I'm saying?
Yeah, that's what it's doing. Yeah.
So it's taking the assignments and it's just using them by hand. Is that correct?
Yeah.
Okay, correct. Fine. Okay, but we need those two cases. We need either a case. Okay, these two cases are merging into each other, right? We have a case where you give the rules explicitly. There's not using the evaluator at all. You have the case where you're avoiding the evaluator by, just using the rules from the down values list, right? Then we've got the case where there is no choice but to use the evaluator because there's no explicit rules because it's in down code, right? So the question is what to do in that case. And then we've got the sandwich case of down code, where even within the down code, it is calling potentially user supplied down values.
Well, we can always, in case of the down code, we can always just splice this trace graph, right? Between when we have to evaluate it.
Well, so
any sub-expression.
In order to make the trace graph, you just call trace on the expression. So unless you had a way to modify trace to be multi, I'm not sure how that would work.
Okay, I have to go. So you guys could keep going actually if you wanted to.
Can I ask as a practical thing about trace graph? I think that that's a fairly self-contained function. Should this at some point be handed off to the graphs and networks team?
They won't do anything with it. It's on you.
Okay.
Okay. I think that we should develop it further. I mean, I think we've got some sort of recoloring to do and so on, but I think, it should make it quickly to the function repository, and then from there into something. I mean, look, what we need to make it practical is we need ways to, I don't know whether we want interactive opening of things or whether we want more kind of the programmatic things that we have in trace. The programmatic things in trace are already useful, right? So this will presumably allow one to trace only a particular function, right?
Yeah, so right now this only is the one argument form of trace. The two argument form, you can give a pattern, and then
I know. So you need a way to represent the kind of,
if we can decide how to hang together like the sparse, like
I know that's what we have to do. So we should figure that out, because this will be very useful for debugging. I mean, if we
and then it could also support all of the same, like trace above, trace below, trace ahead.
Yes, I know, but each one of those things, it's going to be these different kinds of, look, essentially what's happened is you ripped a piece out of the multi-weight graph, actually not even multi-weight graph, out of some kind of valuation graph, and it's got these dangling ends to do with trace above, or the fact that it only saw the Fs and not the Gs and so on. And the question is, how do we represent that? How do we represent those dangling ends? Make sense?
Yeah.
And yes, we should try and address that. Okay, let's see. So any last comments here? I mean, do we have a path forward, so to speak? We know we want to do the purely explicit, not assignment, because that's going to tangle us up with the evaluator. The non-evaluator, you just give rules, which can include two-way rules, and then doing, the observation of the two-way rules, if you understand what I'm saying.
Yes.
Right. Okay, anything else that we need to
I mean, look, we specified a number of next steps here. I think what remains to be done, which we can do in the coming days, is figure out how we're going to, like, what to do next in terms of the functionality that's going to address these multiple different, next steps.
Okay.
Yeah.
All right. So fine. Okay. All right. Well, thanks, guys.